Let's go around the horn, and I'll assume if you give me a go, you've got no instrumentation problems. Booster, go flight. Retro, go flight. Fighter, go flight. Control, Telcom, go. GNC, Ecom, Capcom, go. Surgeon, go. ONP, go. ASD, FAO, go. Network, go. You got everything up? Go.
Hello, I'm Ian Christie, and this is Terranauts. Today we have another episode of A Terranaut's Guide to Leaving the Planet, which is our look at the history of human spaceflight. When we left Project Mercury, they were just finishing up Scott Carpenter's flight, which was the second time that the United States had put an astronaut in orbit. Coming hard on the heels of John Glenn's successful orbital flight, it was proof positive that Glenn's mission was not a fluke, that NASA really had mastered the necessary skills and capabilities to reliably put a human into orbit and return them safely to Earth. One does get the sense at the remove of 60 years, though, that Project Mercury was suffering a little bit of the dog that caught the school bus syndrome. There was a slight air of, okay, now what, to the records that look back on the time. The fact of the matter was that Project Mercury had been conceived and born in a time when the unrivaled Soviet success in space was seen literally as an existential threat to the security of the United States. And so just getting an American into orbit was the imperative that led to the conception and birth of the project. And it was around this goal that not only the program, but pretty much everything about the program had been designed. The original plan, which had now been executed twice, called for a 3-orbit mission. Well, now that had been done. So, what should come next? Well, the obvious answer would be to go for longer flights, to start catching up to the Soviets in terms of the total amount of time spent on orbit. And what was to stop the program from just going on to longer missions? I mean, the up at the beginning and the down at the end were the hard parts, right? Well, not exactly. The 3-orbit design drove a staggering number of other small details about the program. Everything from the number and placement of ground stations, to the number of flight controllers and flight control teams, to the number of ships and aircraft needed to support the recovery of the spacecraft, to a whole host of design features of the capsule itself, had been carefully tuned to the 3-orbital mission concept. And given how difficult the task had appeared to be, and had in fact been, anything which would have been needed for longer missions or more exotic mission objectives had pretty much been jettisoned along the way in the atmosphere of the better is the enemy of the good enough. And I can attest that this is an absolutely essential element when your baseline objective is big, hairy, and audacious. In effect, the decision to focus on a 3-orbit mission had allowed Project Mercury designers and engineers to eliminate a lot of complexity and focus on the essentials. But now to move beyond that concept, they had to reintroduce that complexity, and they had to do it in real time, as it were, because the program was up and running. The designs were complete and had been tested. The hardware was complete or was being completed. Processes and procedures had been designed and tested. Those of you who have been there, I think, can have a sense of just how much energy and time spent in meetings it probably took, even to extend the mission concept to 6 or 7 orbits, which is what was planned for Wally Schirra's flight in the fall of 1962. For those who haven't been there, I think it's worth talking about this process because I think it's a fascinating glimpse into the world of spaceflight and really the world of the Terranaut. So one of the first things we need to understand in order to understand how the 3-orbit mission allowed Project Mercury to really eliminate a lot of complexity is the concept of precession. Precession is a word that refers to the effect that, in effect, when a spacecraft is going around the Earth is rotating underneath it. Now, if you're in a spacecraft going around the equator, this doesn't really have much of an effect. Really, it just speeds up the time it takes to come back to where you started. Because in addition to your speed, you have the added rotational speed of the Earth. And this, by the way, is true because we almost always launch spacecraft to the east against the rotation of the Earth, specifically to gain that extra little bit of speed. However, the only way to launch a spacecraft into an equatorial orbit is to launch it from a location on the equator. Really, this is true. I mean, you can achieve an equatorial orbit from other launch sites, but it's actually really expensive in terms of the amount of fuel you will use to do it. So, why is that? Well, it all has to do with the way objects want to go around other objects in space. If you launch an object into orbit from the Earth, it will naturally want to settle into an orbit around the middle of the Earth, the center of the Earth. So, like if you launch a bunch of satellites from different latitudes, their orbits won't be like a series of rings around the planet at the latitude that they were launched at, which, might be a sensible picture in some ways. No, instead, each satellite will end up in orbit around the middle of the Earth, but the orbit will be canted at an angle that passes through its launch point. And this is called the inclination of the orbit. In fact, the lowest fuel option for any spacecraft is always to launch into an orbit that is inclined by exactly its latitude. So if you launch a satellite from 49 degrees north, its orbit will be inclined at 49 degrees. If you launch a satellite from 28 degrees south, its orbit will be inclined by 28 degrees. Now, you can change that natural inclination, but to do that, you'll be fighting the natural orbital mechanics of the situation, which in rocket speak means that you'll need quite a bit of energy, which is going to mean fuel, which is going to mean weight, not only of the fuel, but of course the containers to carry it. And that's going to mean more weight in primary booster fuel to lift the maneuvering fuel to orbit, and more weight in the tanks to hold that. And, well, you get the picture. So, for Project Mercury, there was really no question that they were going to use the natural inclination of the launch site, which was Cape Canaveral, which is about 28 degrees. So that meant that the Mercury capsule would definitely experience precession as it flew. So back to what that means. Well, let's stand back far enough that we can see the track of the orbit around the Earth. It's basically a circle or ellipse around the Earth at an angle to the equator. So it goes around the Earth at an angle and it crosses the equator in two places, one going south, one going north. Now, if the Earth was not turning, it would follow the same path over the ground all the time, and it would, for instance, cross the same points on the equator each orbit. But the Earth does turn. So, by the time the satellite comes back to the point where it would cross the equator again, it's over a different point on the ground, and we say that its orbit has precessed. How much precession there is in each orbit depends obviously on how long it takes to go around, but it's pretty easy to calculate that the Earth precesses 360 degrees in a 24-hour period, so basically 15 degrees every hour. So if, like a Mercury capsule, you're going around the Earth about every 90 minutes, you could expect your orbit to precess by about 22.5 degrees every orbit. So if we take a flat map of the Earth and we draw the path of the spacecraft over the ground, and you might have seen these diagrams because they're often on the screen in the front of Mission Control when you see pictures from there. Anyways, the path looks like a big looping sine wave across the surface of the Earth with a peak and a valley set by the inclination of the orbit. But the sine wave obviously doesn't reconnect with itself. Instead, the peak and the valley of the curve are displaced by 22.5 degrees every orbit. In this way, the spacecraft will actually travel over, or nearly over, every point on the Earth within the latitude band set by its inclination. Okay, so why would that be an issue for Project Mercury and for going for longer flights? Well, if you remember the episode, a few episodes back where we talked about setting up the Project Mercury Global Network, you'll remember that there were 22 sites across the planet that had been specifically chosen to be optimally sited to communicate with the Mercury capsule for its first 3 trips around the planet. I don't know for sure, but it's a pretty good bet that these were designed to be under, or close to under, the track of the second orbit. And because remember that each of the tracking station could only communicate with the capsule when it was within a certain distance of being overhead. So essentially, the capsule in space had to be above the horizon for the ground site to read its telemetry, or for controllers on the ground to communicate with the astronaut on orbit. So, the farther away that the orbit precessed from the original track, the shorter the communications window would become, until eventually the ground station wouldn't be able to see the spacecraft at all. And for most of the ground stations, this pretty much started happening around the sixth orbit, which means that going much longer than six orbits was going to mean that the astronaut on orbit was going to have less and less support from ground. And particularly, since it would be at the end of his flight, this would happen just at the most critical phase of the flight, which was preparing for reentry. And the first two flights had proven pretty conclusively that this was a time when support from the ground might very well be crucial. Now, there were some exceptions to this rule. For instance, over the continental United States, the ground communications network was dense enough that communications with one of the two U.S. ground sites on either coast was pretty much assured, so Mercury Control could have a good window on just about every orbit. Similarly, control stations aboard ships in the Pacific and Indian Oceans could be changed, or ships could be added to cover more orbital tracks. As well, NASA was now actually able to augment the ground based network with up to five Air Force C 130 Hercules aircraft that would act as airborne relay stations to extend the range of the ground stations, particularly over or near the United States and its territorial waters, or over the mid Pacific from their base at Midway Island. But still, an awful lot of effort that had gone into building the infrastructure of the Mercury Global Network would become less and less useful as the length of the flight was extended. This in turn meant that there would be less and less telemetry coverage, which would give the ground less insight into what was happening on orbit, which raised the stakes on making sure that the guidance and control issues that had bedeviled John Glenn and Scott Carpenter needed categorically to be solved for Wally Schirra's flight. There could be no more entering the last orbit with under 50% fuel remaining, and of risking running out of fuel on reentry because the attitude control instruments and procedures were not working properly. So, a lot of engineering time went into looking into every aspect of the guidance and control system. Actually, to be fair, that effort probably had started after John Glenn's flight, but it wasn't considered flight critical to finish the upgrades prior to Scott Carpenter's flight. After the experience of that flight, the next flight, planned for 6 or 7 orbits, those changes did become flight critical. And these included redesigning the attitude control thrusters and redesigning the control inputs so that the astronaut would be able to much more finely control the amount of fuel they were using and the size of the inputs they were making. The switch panel also had to be redesigned, because both Glenn and Carpenter had found that they could inadvertently put the system into its course rate mode, and that would cause them to use a lot more fuel than they expected for periods of time. There were also a number of training exercises that were designed to help the astronaut determine the yaw of the spacecraft using cues that could be viewed out his one window. But extending the duration of this spacecraft also posed some other issues in terms of the consumables that would be on board. In addition to the hydrogen peroxide fuel for the reaction control system, which was obviously uppermost in the minds of flight controllers, there was also the fact that almost double the oxygen, or more than double the oxygen, needed to be put on board. And also the amount of lithium hydroxide that was used to scrub the atmosphere of CO2 also had to be doubled. Then the amount of electrical power was analyzed, and it was realized that with the batteries available, the mission would only have a margin of less than the required 10% post-landing reserve. And so a number of measures had to be taken to conserve electrical power, including planning to turn off many systems during flight, especially those portions where the capsule was planning to drift. In addition, engineers decided to do things like switching the telemetry transmitter and the radar beacon operations to ground command. And all in all, they found ways to raise the estimated post landing reserve to about 15%. There were also a host of smaller changes, mostly aimed at saving weight and fuel. These included deleting the astronaut observer camera, deleting one of two redundant command receiver decoders, and the whole lower leg section of the astronaut couch, which was replaced with toe, heel, and knee restraints instead. So I mention all of these changes not because they're particularly important in and of themselves, but because they really show the level of attention to detail that was required in preparing for a mission and the amount of very detailed analysis that went into making a change that seemed to be as simple as adding 3 or 4 more orbits to the mission. And the final thing that needed to be analyzed was the issue of recovery, meaning the act of finding and recovering the spacecraft once it had landed. Now, this had been a major challenge on Carpenter's flight, and so it was not surprising that it was analyzed pretty carefully. And it turned out there were two issues. The first was that after 6 orbits, the spacecraft trajectory wouldn't take it over a landing site in the Western Atlantic anymore, where Glenn and Carpenter had splashed down, essentially just a couple 100 miles from home. Instead, the landing site was in the Pacific Ocean, like literally in the middle of the Pacific Ocean. In fact, the nearest U.S. base to the landing area was at Midway Island, which is so named because it is midway between Hawaii and pretty much anywhere. Stationing recovery forces in this area would be a much more significant exercise than had been required for recovery off the Atlantic coast of the United States, because there really were no land bases other than Midway that could have airplanes or ships on standby. The recovery area pretty much all had to be covered by the United States Navy, ships at sea, and aircraft aboard those ships. But then there was another problem posed by the lengthened flight, and specifically sort of the amount of the Earth's surface that could be reached by the Mercury capsule during that time. You see, NASA had a mission rule about recovery. Well, they probably had many rules, but the one that caused the issue was the rule that said that any possible landing site the capsule could reach had to be reachable by some recovery asset within 18 hours, meaning some plane or ship had to be able to get to the capsule within 18 hours of it splashing down. So, when the mission planners sat down and started plotting out all of the possible landing sites and comparing those to the available recovery resources, and they literally found that they eventually ran out of ships and planes that could reach the possible landing sites within the required time. Effectively, once the capsule's trajectory started covering enough of the middle of the Pacific Ocean, there was just too much area to cover. With careful calculation, it was determined that this happened on the 7th orbit. Now, I just for a minute want to pause and think about this just a little bit more clearly. If there was ever a quintessential Terranaut engineering task, it was that of constructing a map of all of the points on the planet that could be reached by a spacecraft, doing a re-entry from any point on its 6 or 7 orbits, and then comparing that to the travel times of all of the ships and airplanes that were, or could be, stationed anywhere on the planet, including based on available aircraft carrier task groups. I mean, you get what I mean. Saying they determined that they ran out of resources after 6 orbits is a pretty short sentence. But behind that is a truly meticulous engineering effort that had to be performed. And given the critical nature of the decision it supported, it had to be checked and challenged and checked again. I can well imagine that some young engineer quite literally spent weeks becoming intimately familiar, not only with the orbital mechanics of the Mercury space capsule, which would kind of be expected, but also with the location and specification of every aircraft and ship in service with the U.S. military at the time, as well as things like base timetables and squadron rotation schedules. Seriously, you won't find it in the sources, but if you've been there, you have to believe that if that gentleman was going to show up and say, sorry, boss, but you can't do 7 orbits, he was going to have to be prepared for a lot of "have you checked" type of questions. And that's what fascinates me, because the success of the program absolutely depended on the engineers that pursued that kind of analysis carefully, completely, and doggedly. Even when there would have been a lot of times when it might have been easier just to say, yeah, it looks okay. But they didn't do that. And even though it never came to matter, it's emblematic of an important attitude and of the culture that inspired it. So, all of which is to say that even though adding 3 orbits to the mission plan for a Mercury mission may not sound like a big leap, it was, in fact, a change which reverberated throughout the program, which is at least partly why, after only a barely 3 month delay between John Glenn and Scott Carpenter's flight, there was actually a 5 month delay before the third mission. And so, eventually, it was settled that the third mission would launch in the fall of 1962, that Wally Schirra would be the astronaut to fly it, and that it would splash down in the Pacific rather than off the coast of Florida in the Atlantic. The other issue that was at the forefront of the mission planning then was very much the okay, now what question of what should be done with those 6 orbits, which is nearly 9 hours of on orbit time. There was actually an even more substantial increase than it sounds, because it wasn't really doubling the amount of available time on orbit. Because once you took out post launch and reentry preparation, there was actually more like 3 times the amount of on orbit time to devote to something. And there indeed was the rub. On the first flight, the engineering team had naturally felt that John Glenn's activities would need to be centered around the spacecraft, its systems, and its performance. And while there was obviously a lot of interest in using Glenn's time to describe and document the experience of spaceflight, he was there to be a test pilot, not the onboard science team. For the second mission, the pendulum had swung back in the opposite direction, and Scott Carpenter had been given a flight plan that called for a significant amount of scientific investigation, some of which had required not only time on orbit, but even time during training. There is no question, though, when one reads between the lines of the commentary on the Mercury program, that the engineering team felt that the focus on science had actually contributed to the issues on Carpenter's flight, and that he had been distracted from his primary duties of flying the spacecraft by the science experiments he was responsible for. Wally Schirra would not be similarly distracted. The way that the flight of Aurora 7 had ended gave the flight control team the feeling that they needed to refocus the flight plan around testing the spacecraft and away from scientific investigations. And the changes that had been made to the new capsule to extend its time on orbit, as well as the need to answer some other questions that really need to get settled if Mercury was ever going to go all the way to staying on orbit for a full 24-hour day or longer, well, those provided all the justification the flight control team needed to write a flight plan that was pretty long on engineering test and verification, and relatively short on scientific investigation. This was a fact that did not go unnoticed by the science community. The conversation between engineers and scientists about who was the ultimate customer for on-orbit time was far from over. It's probably not over today. But the engineers won this round, and so when Wally Schirra headed to the launch pad at 4 a.m. on the 3rd of October 1962 to board his spacecraft, which he dubbed Sigma 7, he carried a flight plan that included a lot of detailed testing of spacecraft systems and flight procedures, and which involved a lot of photography and observation, but not a lot of dedicated science experiment. After a nearly flawless countdown, Sigma 7 left the launch pad at 7:15 and began the first of what was planned to be 6 orbits. There was a brief moment of concern when the rocket began to roll rapidly clockwise, but this smoothed out as suddenly as it began, and the ascent settled down to something that was pretty much entirely nominal. Schirra's first task on orbit was to test the newly redesigned fly-by-wire system of attitude control that allowed him to use just the small thrusters. He found this worked really well and gave him very fine control with the use of very little fuel. He then moved on to trying some of the other control methods that had been redesigned, but eventually decided that for fine control and efficient fuel usage, the fly-by-wire system was the way to go. So that was one major issue that appeared to have been resolved. Other than some small issues with his suit temperature, the first orbit was pretty uneventful. Over the Pacific Ocean, during a night on orbit, he also tested the periscope and declared that, like Glenn and Carpenter before him, he couldn't see schmutz through it. And then, to make matters worse, he had to cover the periscope when the sun came up because the sun shone through the eyepieces and almost blinded him. This news probably didn't bother the NASA engineers overly much because pretty much everyone had decided that the periscope was 67 pounds of excess baggage and they were looking forward to deleting it for the next flight. Over the Pacific, in daytime, he practiced some of the new yaw determination exercises using the window as a reference system and reported that the procedures worked really well, which was another major concern from the first two flights that had now apparently been dealt with. Wally Schirra and Project Mercury were on a roll. He performed a more difficult night yaw test on the next pass, and this was less of a full success. Although he was able to use the air glow layer around the Earth for pitch and roll reference, the system that had been devised for determining yaw, which involved using Starfinder charts to orient himself and Sigma 7 with respect to known stars and the moon, it didn't give him a great deal of confidence, although the ground was able to determine that his error in yaw was actually less than 4 degrees. And during the test, he was also able to determine that there was one celestial pattern that would be very easy to use to align the spacecraft, and that was the pattern to align it to its retrofire position, which was, of course, the only real yaw maneuver that mattered. Basically, he found that if he placed the planet Jupiter in the upper right-hand corner of the window, the double star constellation Grus on the left side of the window, and the star Fomalhaut in the top of the window, he would be in about the right attitude for retrofire. Based on his instrument readings, the ground agreed. All in all, the third Mercury orbital flight was going very well. And so it would continue for all 6 orbits. Wally Schirra's flight is described, in almost all the references I could find, as a textbook flight. There were just enough small anomalies to keep him and the flight control team paying attention, but nothing that compromised the flight in any way. And the flight was also a bit of a public relations coup for NASA. 2 of the 3 U.S. national television networks actually continued live coverage of the flight for the whole flight, even though it meant not covering the first game of the World Series. And during one pass over the United States, Wally Schirra had a live conversation with John Glenn on national TV. As he started his preparations for re-entry, he noted that he had 78% of his fuel remaining, and even after retrofire, he had more than 50% of fuel in his tanks to control his re-entry. His re-entry was not only nominal, but very accurate. He splashed down barely 4.5 miles downrange from his planned landing point, 9 hours and 13 minutes after liftoff, and barely half an hour later, he was aboard the carrier USS Kearsarge. It was exactly the kind of mission that Mercury needed. I see it as actually being a very important mission in the evolution not just of the Mercury program, but of the whole of NASA. To me, at this distance from the mission, and having seen the kind of organization that NASA became and has become, I see the third Mercury mission as developing a very important ability: the ability to adapt. The ability to learn from one mission and actually apply the lessons to the next. The ability to modify designs and even hardware in ways that improve them, but also in ways that are safe and assured. In my experience with the space program, I probably spent much more time engaged in these kinds of activities than I ever did in inventing anything completely new from scratch. Just about everything I did or saw done had an element of using what had worked before and applying it to a new problem. Sometimes it was literally taking an existing piece of hardware and making modifications to it. Sometimes it was taking a concept that had been tested and applying it to a new problem or in a new environment. Often it was just applying a lesson learned from one mission to make changes in hardware, software, or just procedures for the next mission. But in the space business, and as in many other disciplines, I imagine, innovation is often about getting just the right amount of revolution on top of a whole lot of evolution. And the third Mercury mission showed that NASA was mastering that discipline. It was a textbook mission, at least partly because it was devoted to finally resolving some critical issues that had bedeviled the first two flights, and making sure that NASA really did understand the technologies, techniques, and procedures that it was dealing with. It was not an ambitious mission in terms of mission objective. Instead, its ambition was to make sure that even fine wrinkles were ironed out, and that even small but very annoying bugs had been firmly squashed. Because the next and final step for Project Mercury was the biggest one of all, that of having a human spend a whole day, or even a little bit more, off the planet. And that's what we'll talk about next time on Terranauts. That's going to be all for this episode. Thanks for listening, and we'll talk to you soon.
Come on, let's keep the chatter down.